Integration calculus. Integral calculus deals with total change or accumulation of a function over time. For example, if we want to know how far a car traveled in a certain period of time, we can use integration calculus to find the distance traveled to be an integral speed. Some fields that use integration are physics, electrical engineering, and the medicine field. What physics use integration for is heavily relies on calculus to describe and predict the behavior of physical phenomena such as motion, gravity, light, sound, heat and electricity, and magnetism. How it relates to the electrical engineering field is if you could use calculus for calculating the voltage of a current through a capacitor, and integral calculus is also a main consideration in calculating the exact length of a power cable. In the medicinal field, calculus is used to study the absorption, distribution, and metabolism and excretion of drugs in the body. For example, we can use calculus to find the dosage of concentration of a drug that achieves a desired effect or avoiding a toxic effect. That we know what calculus is used for. Let's go to see the history behind who pioneered these ideas and why it's important. Archimedes, centuries earlier, found out about the infinite sums under curves, but he didn't know how to find the geometric proof like many Greek mathematicians wanted to. So he didn't want to accept that this way of doing math was correct until Isaac Newton and William Gottfried came into picture, where they are credited with the modern formulation of integral calculus. It's important to note that that concept of finding areas and volumes using infinite sums has been explored previously, but they built upon their framework to do it better. The development of calculus was not without its controversy. A bitter dispute between Isaac Newton and Gottfield came, each of them claiming that they plagiarized the work. Despite these two guys' conflict, they are both accredited with the co-inventors of calculus. First, let's go over an indefinite integral, which looks like this. It's an integral here, f of x dx. This whatever answer you're gonna get is gonna be f of x plus c, for c is for a constant. Very important that you don't forget the c. That's a indefinite integral. Now, a definite integral looks like this. Goes from either a to b. A and b are numbers. F of x and dx. What you're gonna get out of this one is gonna look like this. You're gonna get a big f of x on that of a to b. Then you're gonna have to do big f of b minus big f of a. Definite integrals always give you a value. Unlike indefinite integrals where you just get an equation plus c. Let's do a quick example of a indefinite integral. So this one's going to be integration sign. Let me rewrite the integration sign of 3x squared or cubed. Sorry. What you going to want to do is integration. So you're just going to ignore this real quick. Ignore the 3 real quick. It's going to be x to the 4th over 4, and put the 3 back. So it's going to be, so you can either write that as that or 3/4 x to the 4th plus c. You know, never forget the plus c. And now let's go over an example of a definite integral using the same number. So it's going to be that. Integration sign from a to b, in this case, is going to be on the interval from 0 to 1 of 3x cubed dx. So what we're going to do is do the same thing. So you're going to get 3/4 x to the 4th dx. But no, you can take the dx out. And then you're going to put this from 0 to 1. You can do f of b minus f of a. But in this case, b is 0, so you'll have to do it because it's just going to end up in 0 anyway. So it's going to be 3/4 times 1 to the 4th, and 1 to the 4th is 1. So in this case, the answer is going to be 3/4. You may notice that um, this equation right here, is actually the fundamental theorem of calculus. Right? Which means is a big f of x prime is equal to f of x, which is which means that it's the antiderivative of a f, meaning that the uh, big F of x is just an inverse of inverse of deriving something. Inverse of a derivative, meaning that they undo each other. Okay, let's do a real world problem that can't be true. Okay, suppose that you're planning a road trip from Albuquerque to Santa Fe. The car's fuel efficiency isn't constant due to factors like speed and elevation. You have a fuel sensor installed on your car that measures the gallon per mile. Gallon per mile, that's important. That's our units. Okay, so this is the function that's measured in gallon per mile. Then, okay, so the interval is going to be on 0 to 60. 0 to 60 because Albuquerque is, in this case, 60 miles away from Santa Fe. So what we're going to do is I'm going to set up the interval of 0 to 60, Rx dx, because you're integrating in terms of x in this case. So it's going to be 0 to 60 of 0.04 minus 0.001 x plus 0.00001 x squared dx. Now you're going to want to integrate it like what we did before on the previous example. So it's going to be 0.004 x minus 0.0001 x squared over 2 plus 0.0000001 x cubed over 3. And that's going to be equal to the big F of x. And interval from 0 to 60. Luckily, our A is 0, so that means we don't have to really care about that because it's just going to equal 0 anyway. But now we're gonna have to take care of the 60, so we're gonna have to do f of x, f of 60 actually, big F, 60 is equal to 0.004 times 60 minus 0.0001 60 squared and divided by 2 plus 0.000001 sorry, times 60 cubed over 3. Doing the calculations on a calculator gives you 2.292 gallons of fuel per mile uh, during during the trip from Albuquerque to Santa Fe. Before I start my next real world example, we're gonna have to know substitution, integration by substitution. This undoes the chain rule. Is if you think about regular integration is undoing a derivative, then you can think of the substitution of undoing a chain rule. How to use a substitution method is, let me give you a quick example. You're gonna have, let me see, the integral. It's gonna be indefinite integral. So it's gonna be x squared plus 1 squared times 2x dx. So you notice that there's a squared term instead of above another square term. So in order to identify what you want to substitute, that's a good way. If there's either like a two terms, so if it was like a x plus x cubed plus x cubed or something to the 100th power, you don't want to do that 100 times. So you could just u sub and let u be x cubed plus x cubed. For this example, that's what you're gonna do. You're gonna use the u substitution on this term because it's in the power in the power. So what we can do is let u equal x squared plus 1. Now you need to find the derivative of that. So derivative of u, so it'd be du equals 2x dx. Now you're gonna solve for that. So it's gonna be, what? Yeah, right there, solved. Right here. Now you're gonna rewrite and integrate what you just substitute. So it's gonna be u squared and 2x, be u squared 2x, but you notice that 2x here and then dx 2x, they're gonna cancel out. So it's gonna be the integral from u to du because the 2x that is equal to du cancels out this 2x right there. Now, now you can integrate. Now you can integrate nicely. So this term is going to be is equal to u cubed over 3 plus c. Remember, you may think this question is done, but it's not done. You still have to plug in what you substitute right here. So you're going to plug that into u. So it's going to be, the answer would be x squared plus 1 cubed over 3 plus c. So that's the answer. We're going to use this for the next real world example. But before I get to that, I want to do one more example of this just for you guys to get it down. Next example, I'm going to use a trig function. This is going to be the integral of 3 sine 3x dx. So what you're going to sub is going to be the 3x because it's in the function of sine. It's in the function of the sine. So you're going to let u equal 3x. Now I'm going to put du over dx is going to be 3dx. And du is going to go 3. Now you're going to write like this. So it'll be 3 sine 3x dx over 3 integral. So those cancel out. So you're just, sorry, it's going to be u. So it's going to be equal to sine of u. Now, since it's sine of u du, you can integrate now. So it's going to be negative cosine. Because into the integral of sine is negative cosine, and you're going to plug back in the 3x. Don't forget the plus c. So that's the answer right there. So I think you should know enough for my next example. This example right here that I hinted at before was that you might have to use substitution. So, okay, let's start. A large reservoir is being filled with water. The rate at which the reservoir, in this case RT right here, is in cubic meters per hour. It's not the constant. The flow is not constant. RT is modeled by this this function right here. Right here. So be using that. Calculate the total volume of water filled from the first 24 hours. Okay, so now we have our interval. So it's going to be 0 to 24. So that's going to be t is equal to 24. So now we're going to do the integral from 0 to 24 of RT, which in this case it's going to be 5,000 e over square root of t squared plus 100 dx. So now you know that we can use the u substitution. I'm going to substitute this term right there. So we're going to put that u equal t squared plus 100, and then du is going to be equal to 2t dx. Now we can do our bounds, our new bounds, because we're in terms of u. So the bounds of t is equal to 24. That's going to go to u is equal to this, and then you're going to calculate that, you just put the 24 into the u, which is t squared plus 100. So that means 25 squared plus 100 is going to be 676. I'm going to do t is equal to 0, which would be u is equal to 0 because u 0 squared, I wouldn't, u 0 squared would be 0, which would be 100. This is the plus 100. So now we have our new bounds. So now we can do the integral from 100 to 676 of 5,000 e over square root of t squared plus 100. But before, or no, sorry, u. But before that, we can actually rewrite this into was it 1/2 t du. Yeah, 1/2 t du. So what's gonna happen since you wrote like that is gonna be times 1/2 p du. So that means that these t's are gonna cancel out, and 1/2 times 5,000 is gonna be 2,500. So up here it's gonna be 2,500 divided by square root of u of 106.76 du. Okay, now we can just plot that 2,500 because you can, it's constant. So that's going to change that into 1 over square root of u du, which means that we can rewrite that into this. It's going to be integral from 100 to 676 of the negative half. Okay, now that we have that, we can integrate now pretty simply. So that's just going to turn into 1/2 plus 1 is be u to the 1/2, and the bottom is just going to be 2 because you flip it. 2 divided by 1 is just 2. This is going to be 2 to the 1/2, and we're going to have our bound, so be 106 and 676. Now you're going to plug that. Now it's going to be plug this one, the bottom one first, so it's going to be 2. Oh, don't forget that we have to plug it in and minus the the bottom bounds to the top bounds. So that's going to be equal to, let's see, 2 to the square root of 100 minus 2 to the square root of 676 times 2,500, because we have our 2,500 still out here. So what you do is you plug them in and you calculate it. So square root of 676 is 26 times 2, then this is going to be minus 2 times, oh, sorry. This one's going to be 26, and this one's just 100. I mean, sorry, 10. Now that we have that, that's just going to equal to 52 minus 20. That's just going to be 2,500 times 32. Now, basically, since this is calculated up here in cubic meters per hour, we know that the final value is going to be 80,000. Sorry, 80,000. 80,000. That means that the reservoir flows in the first 24 hour was 80,000 cubic meters. That should be all for this problem. I hope you guys now understand the importance of integration, some of the backstory of integration, and I hope that my examples come across as understandable and helpful to you guys. Thank you for having me.